So today's video is gonna be a bit different. I'm on my way to EMNLP, one of the leading conferences in AI. It's happening in Suzhou, China, and there are hundreds of researchers here presenting their work. Originally, I was planning to make a video summarizing some of the interesting papers myself, but then I thought, why not let the people who actually did the work explain it to you guys directly? Let's go check it out. So the first paper I'll show you is from Midjourney. The paper is called LLMs Behind the Scenes, and it focuses on a narrative scene illustration, basically automatically generating an image that shows a specific scene from a story. I find this work very interesting because it's easy to imagine Kindle or other e-readers using a feature like this to instantly visualize the paragraph you're reading. But anyway, let's hear about this work from Melissa.
So this work looks at using text-to-image models for generating illustrations for stories. So one of the questions that we focused on is you have a story and there's some part of the story or what we call a fragment that you want to visualize. What should the prompt for your text-to-image model be? And our experiments validate the use of an LLM for synthesizing what we call the scene description or the prompt. We run our experiments on the basis of this pipeline, which produces a data set on the basis of pairs where each there's two images that are corresponding to the same fragment, and people are asked which of the illustrations is a better visualization of the fragment. So on the basis of that data set, we do analysis looking at how important is the LLM in synthesizing scene descriptions. We compare it to some baselines that look at the story text more directly as the prompt, and we find that people prefer when the LLM is used to synthesize the scene descriptions. We also look at LLM's ability to contribute to the process of modeling these illustration quality judgments. So to do that, we have LLMs synthesizing criteria. These criteria define the individual expected and visual features of an illustration, but importantly, for this criteria generation process, there's no image being provided to the LLM. It's just writing this criteria on the basis of the fragment. So we have LLMs generating these criteria lists, and then VLMs, so models that are able to take images as input, can assign responses to the criteria. So yes, no, maybe, to the question of whether the criterion is satisfied by the image. And we find that this approach to evaluation is more effective than a baseline that doesn't utilize the criteria.
A general question. What's the practical application of this? Do people like to see images when they read text?
So I haven't done a survey to find out to what degree people want this, but you could imagine an app where it's like an e-reader and people can select text and have it be visualized as an image, as a way of gaining more insight or a different perspective into the story that they're reading.
Right.
Yeah.
So interesting. Thank you so much.
Yeah.
The next paper is also about vision, but this one focuses on hallucinations. The authors show that vision language models can be easily confused when prompted with something that actually is not in the image. And what I find especially interesting is that there seems to be a group of neurons that behave consistently different when the model is exposed to these visually absent tokens.
We are observing the large vision language models, and if we put the large vision language model with visually absent token, this token means that the token that does not align with the image. For example, in this example, the woman is sitting, but in the question there is the term standing. So if we put these kinds of questions, the model easily tricked by the standing word, the visually absent token, and they just simply follows the question. Yes, the woman is in the image, is standing outside. But if we ask the same question, but without visually absent token like this, what is the woman doing in the image? Then the model just naturally says correctly, like the woman in the image is sitting on the bicycle. So we thought that the model easily tricked by such visual absent tokens, but is that model doesn't know, or they even knows they output the wrong tokens. So we constructed the data set called VAQA, and there's the existing data set that is paired with the image and the question like this, and we just simply flip the one object or subject or verb. For example, in this example, the paired question is the dog lying in the middle, and we change the middle to the bed. And this question, when image A and question B comes into right, the answer should be no, and bad is the visually absent token for image A. So we can collect the visually questions with visually absent tokens, questions with visually present tokens. Then we collected the activation values of these tokens, and we observed that in some neurons, there is the activation value deviation like this. In visual absence aware neurons, there is such disentanglements like this, and the other neurons, there is no difference between the distributions. So we just simply measure the disentanglement separation between these distributions as Bhattacharya coefficient. That's the very standard coefficient. And we chose the neurons with high this score, VA score, and we just simply collect the activation value of these VA neurons and train the VA absence, visual absence detector, which is 2-layer MLP. And we train them to classify visually absent or visually present. Then using that visually absent detector, we refine the output of the LVLM. And in binary QA, if the visually absent token is contained in the question, the answer should be no. And when nothing detected, it should be yes. And in open-ended generation, when model is generating some tokens, if the one token is detected as it is visually absent, we just roll back and choose the another token, the next most probable token. And when we refine the answer like this, we show very consistent improvements in 6 models.
What proportion of the neural net is usually used for the activation?
We observed that the neurons in the middle layer, not the lower layer, higher layer, the middle layer mostly detect the visual absence of the token.
Okay.
Yeah. And the neurons, the position of the neuron is different depending on the model.
Right.
Yeah. Yeah.
Thank you so much.
The last paper is called Fooling the LVLM Judges. Similar to the first Midjourney paper, this work also deals with text-to-image generation, but here the focus is on a very popular idea in AI called LLM as a judge. In this setup, you're not using LLMs to generate content, instead you use it to judge outputs. For example, LLM judge might look at the prompt and a previously generated image and give it a score like 3 out of 5. But the authors show that these judges can be negatively influenced by simple visual manipulations like the overlay text here, which can trick the model into giving it a higher score. Well, let's hear more from the author. And by the way, I'll be releasing 2 more videos from the conference on different topics, so subscribe if you want to see more.
Okay, so our motivation is really simple. For, as you know, like recently, like LLM judge has been used widely, and this paradigm of LLM judge has been adapted in the like LLM domains. So recently, like LVLM for increasingly used for like automated judges for text to image alignment in T2I evaluation, and the robustness of like LVLM judges to like image variation is underexploited. So we test whether the image side biases can affect the LVLM judge system. So basically, as you can see, LVLM judge get the evaluation prompt and the instruction that is originated for the image and each image for like this. And we test whether the image side biases like maybe putting the instruction overlay can affect the evaluation output. So
The overlay is this text, for example.
yeah, this is text example. So we predefine like 8 visual biases like this. So bounding boxes and like authentic, like overlaying, keyword overlaying, and instruction overlaying, and like black box, beauty filter, like gamma correction, brightness adjustment, and so on. And here's the main result of our paper. So basically, this column in original is the original evaluation score that every LLM has been outputted, but and you can see like each column shows the evaluation output, that average evaluation output that every judge have been outputted after the image fed biases has been adapted. And so as you can see, both the LLM judge are constantly vulnerable across like domains and bias types, and the manipulated images receive higher alignment scores than their originals. So this can be problematic because like malicious like attacker can post-process their generated image to get the higher score than the original. So, and also, as you can see, our one finding is that like model 5 does not guarantee the robustness of the LLM judge. So for example, as you can see, like the output of GPT-4o mini and GPT-4o of attack surface rate is similar. And also, we tested some mitigation method that might help the LVLM method judge can maybe help to figure out. And as you can see, like bias-aware prompting, which like prompt like LLM that the definition of each biases, and the COT prompting, like which ask LLM to first like think and then generate the output. But as you can see, the score are still inflated. Yeah, so it's still vulnerable against the biases. And finally, we tested the pairwise evaluation. So basically, this purple is the upper graph is the pairwise evaluation win lose rate of like model A and B. But when the bias is applied in the purple output, as you can see, the win rate of the purple model is highly preferred. Yeah. So this can be also really problematic because like since the models like scores can be really affected by the visual size biases. So these are the three contributions of our paper. So basically, we are first to provide the systematic study of image size biases in LVLM-based evaluation, and we show that like recent LVLM judges, including like state SOTA model like GPT 4.0, is still vulnerable to image biases. And finally, like this vulnerability persists across tasks and resistance to like common prompting defense and in the like pairwise evaluation method. Yeah.
What do you think is the best strategy to deal with these problems?
Yeah, I think based on this our like simple mitigation method, the prompting does not work. So maybe we should like use the fine-tuning method maybe to get the more robust LVLM judge system. So
Thank you so much.